So this is a technical introduction and a little bit of a preview of YAAA, which is an assignment algorithm that I've been working on for the last year now, and it's starting to get to the point where I want to show it off and show what it can do and explain its features in a little bit more depth. So this is a video I'm making to show that. Obviously, this is pre-alpha. There's nothing permanent about this implementation, but it's starting to get close. All right. So the point of YAAA is to be a traffic assignment algorithm that's fast, flexible, and modern. We can put this anywhere, and we can really use it to solve not just traffic assignment, but more general problems in the same problem class. But the first class thing that this thing is designed to solve is traffic assignment problems. So we first need to define what they are. So traffic assignment is the process of assigning vehicles to a network and the paths that they take such that no individual vehicle can get from its starting point to its endpoint in a way that they can reduce their total travel time. So let me explain through an example to hopefully get you through why this is hard. So let's imagine you and like 10,000 of your buddies are at node A and you all work at node F, okay? And this is a network of road links between them, okay? You might start off by going, oh, we'll just take the shortest path. I'll go from A to C to D to F. That's the fastest way from F. Everyone knows it, okay? But if you all know that, now you're getting congested. You're getting in each other's way. There's traffic jams are backing up. And suddenly this path is much slower than a much faster path, like A to B to F, okay? But now you have, 3,000 of your friends notice that, so you all start going A to B to F. And now that path is also congested. So the goal of traffic assignment is really solving all the paths so that no person can find a faster alternative route between A and F. But even this is a simplification because the network is much simpler. We have whole road networks going of a whole city or even a state. And then you have people starting from many origins and many destinations. So you might have someone going from C to D. You might have someone going from E to B, all at the same time, and you're trying to balance this whole system so that it hits that condition. Right? So, as I previously stated, I made YAAA to really solve this traffic assignment as quickly as possible, but I also wanted to make sure I implement this thing general enough that there's a variety of other problems that this could be used for. Okay. Here are a few of so there exists other packages that do this type of problem, and none that are widely used that natively work on a GPU, but my implementation has a few advantages, okay? So first of all, it's in PyTorch. I'm not going to go through every one of these sub-examples, but you get the usual benefits of being able to modify this thing, change it, integrate it with other Python packages quite easily. A lot of the other solvers, they're really locked into a proprietary software framework. I have a more flexible representation of demands. So it really, hopefully, in traffic modeling specifically, you can remove TASers as a concept that you have to deal with. But it also leaves it open up to other problems that can really be helped with. And finally, it's got a much more flexible representation of the network itself. And I'll get to that later, but that is probably the most exciting and most important part of this thing. But there's lots of other reasons you do it even without explaining to that hypergraph stuff. So this is an example I have. It runs on a really simple 4GB GPU, like quite a cheap laptop, but yeah. So we read some data. I've done this whole thing. We encode the network, yada yada. So here's the solving part. You can see it runs on a GPU if you want to see it. All the way up using pretty much the whole GPU. That's a little bit lower. Yeah, okay. It solves relatively quickly. This network is quite inefficiently encoded, but it still does a good job at solving it. And then we can see these results. This assignment only started at 2 places, so the orange nodes are the start and end nodes. So you can see it comes here. Pretty much everyone goes down there, but then they spread out far enough and they get joined up at the end here. So you see about 10,000 people come here. The algorithm works as you expect. We're working currently on some convergence criteria to make sure this thing is rock solid and can be used in all use cases, but it's pretty robust right now, and we're going further. Okay, so if your only takeaway and all you need to know about this thing is that the GPU implementation of traffic assignment, that's great. You can take that, you can call us up whenever you have a really big network or a really hard problem that you need to solve. But in my opinion, that's the least interesting thing about this thing. There is so much more to solve. There is so much more nuance and beauty in this algorithm. So one of the things I have changed with this implementation is how I represent demands. So usually with demands, we take out like about 1,000 to 3,000 nodes out of what might be like a 10 or 100,000 node network, and we create what's called an OD matrix, where each row represents the index of a node, the origin index, and each column represents a destination index. And so this matrix represents where vehicles are going, where they're starting, where they're ending. And the reason why we do this is because the computational complexity of this problem grows with the number of demands, with the number of demand nodes. So if you try to apply demands to every single node, uh, the algorithm would grow at n squared. You'd run out of runtime. Everything would like fall flat on its face. Right? So because of this limited sets that we apply nodes to, we end up doing this thing called TAS connectors. And they're sort of additional assumptions and we do to the model to simplify the computation. And what we do is we pick a node, we make up an imaginary node, and we connect it to various other nodes around this TAS connector node. And the reason we do this is because if we tried to put it all on one node on a random back street, that street would immediately get congested and it wouldn't be a very good model of what we're building. So by doing these connectors, we sort of get around this problem. But this adds a lot of complexity. We like read networks and we have to build a script for modifying the network that we come in to add these. What if the input network changes? We have to revalidate. There's more links in our network, so it suddenly becomes slower to route again. This whole thing hurts our modeling efforts substantially. So the solution that this model comes up with is very similar. It's a very similar representation. But the idea behind it, it just gives you a little bit more flexibility and allows us to sidestep this mess. So in my representation, what we do is we start up with a list of nodes that we have, like same as a subset, but this subset can be as big as it wants without introducing extraneous runtime delays. And all it does is that each row represents where vehicles start and where they end their trips, and negative represents where vehicles end their trips, and positive represents where they start, and each row should add up to 0. So so in this example, DAB represents the net change of vehicles at this specific node. And each row in this is kind of equivalent to a TAS, where it's like a routing class. We call it a routing unit. And the idea is every vehicle in here is sort of fungible. So if two people were commuting and you swap them over, they would still do the exact same thing. All right. So hopefully it's a bit of an opaque definition, but in example, it should be quite easy. So in this example, we have 10 people going from A, 10 people going to B, 10 people going from A to D. But if we wanted to change this so that we had one person in place A, and we wanted 5 of them going to B and 5 of them going to D, we could quite simply just go here, append, so we go B here, and then we go change this to -5, -5. And now we have 5 people going from A to B and 5 people from going to A to D, and that's no more cost. Now, this is normally how TAS zones work. This is the same computation or ability, but where this really starts to shine is when you have multiple people starting their trips in slightly different places. You can do this without creating a whole new routing unit. So we can simply just add, let's imagine 2 people coming from D and 8 people coming from A. This would really give us a much better representation. It gives us a much more nuance, and it does this without blowing up the computational runtime that normal TAS connectors can do. So you still have to have many routing units, but it gives you a little bit more flexibility, lets you sidestep the whole TAS issue, and everything is nice. The other change I made, and the much more substantial one, is that I really changed how we represent the network. So normally we do this just as like a typical graph that we use in computations. So it's just a bunch of nodes with connections between any pair of nodes. What I have done is I've generalized this a little bit, so you have collections of nodes that have a relationship with each other. And the reason why I did this is mostly because it started off as a jealousy of computational fluid dynamics. So when other people build models about airflows around aircraft and stuff, they have this ability to really increase the resolution around really minute, complicated areas, but then there's broader, further away areas that they don't really care about, that they really reduce their computation for. And I want the same feature in my traffic demand models. This would allow us to do something like have a whole country assignment model, but then it gets more and more complicated, more and more nuanced, more and more correct assets, just more detail as we zoom in on our area, like arbitrarily so. So because of this, I sort of substitute in and I say, hey, we can represent a whole area with one hyperedge. And all the hyperedge is just a function, okay? It's just a function, and in this case, it's actually on OD demands, okay? So because we have to fully represent E and E by itself to everything else, we use just the matrix as OD demands, okay? And this just translates it to travel times, so that if we had 1,000 people going from E to B, the travel time from E to B would be increased. If, let's imagine, A to D used this link normally, uh, their travel time would also change from E to B increasing. Uh, it, the idea is it captures the whole relationship between this network. Okay, and as I said, there's lots of advantages to doing this. The idea is that it sort of gets steps around the curse of what our static assignment models are, which is that we we limited to these like uh, one link E to G, like that's the impact of the road, and we can start putting in much more nuanced, much more representative demonstrations of traffic flow through our networks by substituting these hyperedges. Like, for example, you could build a neural network that approximates the solution from a DTA model just by running the DTA of many times with many different demands, and you could just plug it into this hyperedge, and since it's just a function that'll be differentiable, the whole model can solve. Okay, so there's lots of examples of this. Like an immediate opportunity that came when I was just building the test case for this is that Overture, that is what I'm using as the base network for this example. It doesn't give you a single links as a thing. It gives you whole corridors. So it'll give you like many nodes as a input, which is great. But in normal traffic assignment scenarios, we have to then write some scripts that'll break this up or use some other third party tool. We have to start making assumptions about like where the lanes are and stuff. There is no reason why we can't just natively build a function. So hopefully you can see this here. This is a hyperedge, a single hyperedge, and it has a single cost function uh, with various parameters. And all it is just takes the places where the link is split according to this connectors attribute. Okay, and so because of this, we can really just natively just assign a network that works. And as you can see, all the cost function is just a function on some demands. So if I have 999 demands, you'll see this top row, A to Z, just increase thing. That's why it's 10 to 7. If I decrease it, if I go down to 1, you'll see it decrease. If I change it to 10, we have capacity of 10, so expect them all to be double. Uh, all it is just a function that translates your demands OD matrix into a matrix of travel times. Okay. Similarly, just for communication, we have this thing. So if you this represents the segment that I encoded, but hyperedge is a very general idea. Okay, and as I said, it really helps you work things out. Okay, so I have a few examples of this thing running. If you want to go through, I can send you this notebook, but it goes through all the examples of multi-user classes, Bray's paradox shows it working with that. Shows that it goes through all the usual use cases. Okay, so memory requirements. So one of the reasons why you would use this over a normal solver is performance. Okay, and currently it can get you your assignment relatively quickly. Uh, the general rule of thumb is that if you can fit this on a GPU, it can run an iteration in a few seconds, get you your result in about like 50, 100 seconds. Right now, it's a little bit memory hungry, particularly with this 1.5. So this is a rough approximation, but that's 1.5 to the number of hyperedges. This is effectively makes the whole algorithm all 1.5 in terms of memory. You could still fit a relatively large network, so 200,000 length, 3,000 TAS nodes on sort of a H200 tensor, like a H200, which is the most up to date that NVIDIA has to offer. In the near future, there's no we're really expecting to be able to get this down to a linear term, And that can really fit, 15 gigs of RAM now, so we're starting to really compress this thing down. And maybe we'll get even more improvements than that, but we can expect pretty good performance in the future. This is very close. So that brings us to the roadmap and what I'm hoping to do in the future. Uh, Immediately, I'm trying to just get this thing so that someone can use it for practical problems. So currently, you need a little bit of finicking around to make sure this thing converges. We should be able to automate that out and make it so it's very reliable. The API has some improvements and some things that I want to move around such that the user can really use this thing to its full power and just do whatever they want with it. Yeah. And various other things going into the future. But further on, there's a few things. So as I talked about in the HyperEdge, the network representation of the model that I'm showing, I really want to prove out this what I'm calling network distilling, where we get a whole area, like a whole state or a whole county or whatever, and we just distill it into like some other function, and that approximates it to a reasonable degree that we can use to solve our models correctly much quicker than we normally can. Okay. Uh, there's various other features that will go in terms of, we should be able to use transit assignment because we have these generalized functions. There's no reason why we can't just have any type of transit behavior we want. Various other typical features done for traffic assignment. This is a very interesting one, is we want to prove co-optimization use cases. So because this is simply a PyTorch model, and PyTorch framework literally just says, tell me what to optimize and tell me what to optimize against. Tell me what I have to minimize these parameters to do. We should be able to solve certain parts. We should be able to have parameters of the network itself, or of the demands itself, that are optimized with this case. So you should be able to design with this thing a bit more, rather than trying out something, waiting for assignment to solve, looking at the answer, and then iterating until it do it. We should be able to just say, hey, here's a toll on a road. Let's change it. Let optimize it so that we get optimal behavior along the whole network. Hey, here's the number of lanes with this thing. What if we reduce them? What if we increase them? Optimize the whole thing depending on these conditions. And the eventual place that I would like to be much further on in the future is have like a DTA. So that's called dynamic traffic assignment. And the ideal version of this would be something that works as well, where you can build a DTA model very quickly, where you're measuring every second of where vehicles are, where they're traveling, and you iterate through time. So it's a really dynamic model. And you should just be able to change a couple lines of code, and the whole thing would work as a fluid flow model, like as I said above. So that's what I was saying about how it's general to a variety of problems. Sorry, I'm just trying to show you. So you should be able to change a couple of parameters around and have this thing work like a fluid flow model. There is no reason, if it's just things moving through a network or things moving through a set of cells, uh, and a condition that you're trying to minimize, you could potentially do that. So that's the state of the art for this thing. I really want to improve these features in a few months, hopefully, and then I want to start sending it out to people and really start seeing like how they can use this thing and what they can do with their research. But I think this thing's very exciting, and I'd be very interested if anyone wants to get in contact with me about this thing and how this works.